Okay, so we got our three simple facts about vectors. Hopefully you gravitated or attached immediately to some form of writing them down. Here's what we're going to do. And I can change mine. So I like to just write x comma y, right? You could say that's the x component of vector A and the y component of vector B, or y component of vector A, excuse me. So we have x and y. The A vector will have 4 units in the x direction. So watch. We draw it. And we just count 1, 2, 3, 4. Maybe make a little mark. And then we have to count 3 up. So if we want to draw vector A, we're going to do 4 over and 3 up. And we draw an arrow. And just say, whoop, there it is. There's vector A. What's the magnitude of vector A? By the way, I bet you didn't notice that. On the previous slide, real fast, the word magnitude should look like it has absolute value bars around it. Because if I want to specify, like, okay, I have a bunch of vectors, or I'm doing this geometry stuff, and I want to specify, I only want the length of the vector, its magnitude, its absolute value sign. Yep, it's 5. Because it's a 3, 4, 5 triangle. Okay? Sometimes you have a really simple vector, b. To draw vector b by itself, you just draw straight up 3 spaces. Vector b has a magnitude of just 3. Oh, the absolute value goes around b, and then that's a scalar, so I don't need to write anything over there. It's just 3. Awesome. How did you know that the hypotenuse, the magnitude of the vector, would be 5? You did. It's a Pythagorean triple. You did Pythagorean theorem. So what I'm doing to go from components to magnitude is just doing the Pythagorean theorem from geometry class. Okay. Square the x, square the y, add them together, take the square root of the total. Okay, it's super easy when it's 0 and something else, because, wait. You just write the number without any pluses or minuses. Did you know Pythagoras didn't make up Pythagoras' theorem? He learned it from the ancient Babylonians, who were around back then. Haha. He's getting famous for nothing, just like IJKs. They're famous just because Einstein liked them. Anyway. Okay. Here's the trick. To add geometrically a plus b, what do you think you do? Is it obvious? What do you think?
Okay, what I like to do is I put B kind of on top of A and then I draw the line.
Okay.
B and then I calculate that.
It's a little more specific than on top, but give me a thumbs up if you've heard this before. This is old news? Oh, just like half of you, maybe half. Okay. You can draw them nose to tail, it's called. The arrows have a nose and the arrows have a tail. So if I want to draw a plus b, then I have to draw vector b starting at the end of a. Okay, 1, 2, 3. So there's b. Right? And then I have, let's see if you remember this. I'm going to call it r in the middle for the result, or resultant vector. Okay? Now, mathematically, what did this accomplish? Can you spot it on the board? Sure. I just added x's to x's and y's to y's. Oh, exactly. And I just did a picture of it. Perfect. Okay, now if a plus b equals r, I'm going to look silly for a minute. Does r equal b plus a? If I wrote it backwards, am I really questioning like the This is called the transmutative property. I think so. Maybe it's not transmute. Trans something property of addition. Well, of course it does. But this actually means draw vector b first, and then draw a on the end of it. But the result is the same. Geometry. Okay? That's sometimes called parallel addition. Or parallelogram addition, because it makes a parallelogram. Right, you end up with these parallel sides, and the resultant is the diagonal of your parallelogram. Isn't adding vectors fun? It's good that adding is fun, because if we have some acceleration involved, we might actually have to subtract them. Okay, any questions? Okay. Buckle up. What would we get if we did a minus b? Now I deliberately made vector b a different color, vector minus b. So original vector b is just 0 for the x component and plus 3 for the y component. So minus b, if I have enough room, is actually negative 1 times b. So this is not just b subtracted or b anything. This is a new vector. It's actually, it happens to be equal to negative 1 times b. But it's 0 minus 3. So the first thing we have to point out with vectors is that a minus b doesn't really mean anything. You're actually supposed to say vector a plus this new vector that we made, negative b. Wrong color. We could even put parentheses around it. Minus b. Okay. And I'm super interested, does that equal minus b plus a? Are they even equal? Let's draw it. Oh no, I mean, rats. I mean b minus a. Of course they're equal if I did that. Because that's the same nonsense. What if I took vector b plus negative a, b minus a? Let's do that. Oh, I should have written that plus there too. Okay, maybe I need a plus sign there. So, vector a is over 4 and up 3. It's our super fun Pythagorean triple that I use a lot. And then I take minus b on the end of that. And sure enough, if I subtracted the 3 from vector a on the last page instead of adding it, okay, I get the result. And we can do superscript a minus b, or subscript, equals just plus 4 and then 0. On the other hand, to do negative a, I got to go back 4 and down 3. That's negative a, negative 1. Negative a vector, it's minus 4 and minus 3 with my square brackets, angled brackets. And then I'm supposed to add b to that. Oh no. So I can add any order. I could have done the parallelogram for each one, but it actually matters when you're subtracting. We'll call this r b minus a. back that way. So no, they're not equal. So it's the most bizarre thing, and I think unless you draw it this one time, one day, to take a brain break from computing all those crazy problems, I think it won't sink in. You have to be really careful subtracting vectors, because a minus b does not equal b minus a. Those negative b's and negative a's are actually whole new vectors that are reflected through the origin. So you have to give everything a minus sign. Invent a new vector. You could rename it if you want. Some math professors will just say, oh no, this is brand new, I'm going to call this C instead of subtracting B. Well, problem is, chapter 4 we're going to get into different forces, and forces add and subtract and balance out, right? Gravity's pulling me down, how come I don't fall down? Well, the floor is pushing up on me, obviously. If you fall down and hit the floor, it hits you back. We'll stick to obvious things, but we're going to need to add and subtract vectors next chapter. So today, in chapter 3, we're going to use the vectors. Okay, any questions? Okay, just be very careful with subtraction. Let's put that in red. With vector subtraction. Okay. Okay. Luckily, usually we just do stuff like this. We do what's called resolving the vector. And once we do that, we just use our physics stuff for what's parallel to x and what's parallel to y, which is really important. It's why it's so important to have vectors in the first place. Because if I just break off the x and y components, then no problem. Okay? So if I kick a soccer ball that has starting velocity 20 meters per second, and it's at this magical, I'm going to say 37. I love my 3, 4, 5 triangles. Maybe I'm a reincarnated ancient Babylonian. But I know it's really 36.87. Just pretend like, oh, I'm going to give you, now's a good time. After I finish writing this, I'll pass out the chapter 3 equation sheet, and it has these shortcuts. Like, so when I say an angle's about 37, I mean it's exactly 3, 4, 5. Or if I say it's about 53, the complement of that. I want exactly 3, 4, 5. Okay? Predict the motion. Okay, well all we have to do is say the velocity in the x direction, so I've got this vector, it's got magnitude of speed and direction, 37 above horizontal. Okay, so I just have to say v0 cosine of 37, and I mean 36.87 or something like that. Yeah. What's the cosine? If it's 3, 4, 5, 3, 4, 5, I think that's 16. Okay, and I can do Vy. Would be this side of the triangle. Vy equals V0 sine of theta. Sine of the angle, excuse me, 37 degrees. Okay, and that should be, oh, did I do it wrong? No, 5, 4, 3. That's 12. Okay, so it should be 12 meters per second. Okay. Awesome. So then I can just say, okay, my velocity is v0 is plus 16 in the x direction, 16.0, and plus 12 in the y direction. And does gravity accelerate anything sideways? No, not in our experiments anyway. So we'll just leave that one alone. That has a constant speed of 16 meters per second. And then if it starts up at 12, it's just going to accelerate down at 10. And so you can plug in all the equations that we did for chapter 2, and that's it. You just split them. Okay? I won't make you go through all the predictions. We'll stop that there. Oh, just under 15.